Hi, this video is about doing binomial hypothesis testing using the new distribution menu on the calculator, and we'll start with one-tailed tests. So let's read through this situation. So a television company believes that the proportion of households that can receive channel C is 0.35. And we have a random sample of 14 households, and in that 2 can receive channel C. So that's what we're really interested in. Test at the 2.5% significance level whether there's evidence that the proportion of households that can receive channel C is less than 0.35. Okay, so we need to start by writing some hypotheses. So we start with our null hypothesis. So that's the status quo. So null hypothesis is that the proportion of households that can receive channel C is equal to 0.35. Okay. And we're really interested in whether the proportion of households that can receive the channel is less than that. So that's our alternative hypothesis. We also have to define P. Okay, so that I'm just copying words straight from the question there. You could put probability instead of proportion. Okay. So now we need some data to test this, and our data is the 2 that can receive channel C out of the 14 households. So I'm going to write down first of all what our data is going to be. Okay, so I'm saying that X is the number of households that can receive channel C out of 14. Okay, and then we can say that we've got a binomial distribution with 14 trials, and the chance of success always comes from the null hypothesis. Okay, right. So we want to find the probability of getting something at least as extreme as 2 if that null hypothesis is true, because then we'll find out how rare it is, and we can decide if it's too rare for us to think that the null hypothesis really is true. Okay, so we're going to find this probability. We always look at the same tail as the alternative hypothesis. So we're going to have a less than or equal to there, and our data is 2. Okay, so I'll just put that sign in. So hopefully you can see here that whatever symbol we've used in our alternative hypothesis, we use the same symbol for the at least as extreme as, okay, and then we also put equal to, because it can be as extreme as 2. If we illustrate that, okay, let's just have a little bar model. So here's some kind of binomial distribution, okay. We're going to find the chance of getting something at least as small as 2. So here's 0, 1, 2. So we're finding this probability here, and then we're going to decide, is that too rare? Okay, so let's get the calculator, and we go down to the distribution menu. Okay, and we want a binomial distribution, and we're looking in the less than tail, so that's F1. X is, in fact, 2 here. Our number of trials is 14. The chance of success is 0.35. Okay, and let's have a look at the picture. So it's drawn this that we've drawn on here as well, and we can see this is our probability. I'm going to press options F1, because then I can just check that it's rounded correctly. So the probability we've got was, oh, I've just forgotten it, 0.0839. Okay, now that's like an 8% chance. Is that sufficiently rare for us to say that the null hypothesis is wrong and actually you've got less than a 35% chance of getting channel C? So the decision is made by the significance level. Okay, so that was this 2.5% significance level. So we compare our 0.0839 with 0.025. Okay, there's our 2.5%. And obviously this is definitely greater than that significance level. So if I was drawing my significance level on here, it's going to be somewhere over there. Okay, and that's a much rarer thing than observing 2. So we would say there's insufficient evidence to reject the null hypothesis. So if our p-value, our probability of getting something at least as extreme as 2, is greater than the significance level, we don't have enough evidence to reject the null hypothesis. Okay, so that's what we write. Okay, now we need to put that conclusion in context. So we've done this quite mechanical thing with our hypothesis test. We now need to put it back so it makes sense for the question. So it means that it is unlikely that the proportion of households that can receive channel C is less than 0.35. So when I put it in context, if my conclusion was there was insufficient evidence, then it's always unlikely that the exciting things happened, and I copy words from that question. Okay. Right, so here we have a different situation. Let's see what we've got. So 55% of the pupils in a large school are girls. A member of the student council claims that the probability that a girl rather than a boy becomes head student is greater than 0.55. Okay, so that's what we're really interested in. So that will be our alternative hypothesis. As evidence for his claim, he says that 6 of the last 8 head students, okay, have been girls. All right. Use an exact binomial distribution to test the claim at the 10% significance level. So as ever, we start with our hypotheses. So let's go. So our null hypothesis is the boring option. Okay, which is that it's no different from 0.55. So the probability is 0.55. Our alternative is that it is the thing we're interested in, which is that it was claimed to be greater than 0.55. Okay. We have to define what P means. So P is the probability of a girl being head student is the probability of a girl being head student. Okay, so now we look for data, and the data is 6 out of the last 8 head students have been girls. So X is the number of girl students, number of girls out of the number of head students. Okay, and that has a binomial distribution with, we're out of 8, so n is 8, and the probability of success always comes from the hypothesis, the null hypothesis. Oops. So now we want to find the probability of getting something at least as extreme as 6 girls. Okay, so in this context, we can see that we've got a greater than for our alternative hypothesis. So that means that we are going to use greater than or equal to be at least as extreme as the 6. Okay, so I'm going to draw myself a little binomial distribution again. Okay, and I'm going to go, oh, I might have drawn too many. 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I went slightly too far. That's it. Okay, so we're looking at the probability of getting something greater than or equal to 6. So we're looking at this probability here. That's what we want to find out. We're then going to compare it with the significance level. So first let's find that probability from your calculator. So exit, and we exit because we want to change the number of trials and the probability of success, and in fact x. So we want to do greater than or equal to, we want to do 6, we want to do number of trials as 8, and the chance of success is 0.55. Okay, so let's go. So let's look at this probability. So 0.220. Okay, so that's what this blue bit over here is, 0.220. Now our significance level is 10% this time. Let's just have a look. 10%. Okay, so if we had our cutoff for that, that's going to be smaller somewhere, isn't it? Okay, so we need to compare our p-value, our probability of getting something at least as extreme as 6, with our significance level. And we know that it's greater than. So again, we have insufficient evidence to reject the null hypothesis because our observation of 6 is not that extreme out of 8. Yep. We'd need to have a 7 or an 8 perhaps. Okay. So we put in our decision, insufficient evidence to reject the null hypothesis at the 10% significance level. Okay. And we also know that we can know that we need to make a conclusion in the context. So that means it is unlikely that the probability of a girl being head student is greater than 0.55. Okay? Right. So it's very important that you make that comparison nice and clear. All of the steps I'm putting in are kind of the least you should be putting down for any hypothesis testing. There's no need to put loads more either.